This video is the second in the series on extrema of functions. Here we look at the first derivative test. We'll be assuming that you've already looked at the video on critical points of functions. Before we get into things, remember that local maxima and minima occur where the curve appears to change direction. In other words, where the curve changes from increasing to decreasing, or the reverse, decreasing to increasing. The first derivative tells us about whether the function is increasing or decreasing. So we can use the first derivative's value near critical points to either side of it to tell us whether the function reaches a maxima or a minima there. To put this a bit more formally, we've got the first derivative test shown in this here table. Let's say we have a function f of x with a critical point at the x value x equal to c. What we need to do is evaluate the first derivative of f a little bit to the left of the critical point and a little bit to the right of the critical point. In other words, we'd be looking at f dashed at c minus a little bit. Sometimes in mathematics we say epsilon. And then looking at it on the right, f dashed at c plus a little bit. Again, c plus epsilon perhaps. Now there's three possibilities that we can find here. The first one is that we find a local minimum. Now f of x will have a local minimum at our critical point x equal to c if its derivative changes from negative to positive. So in other words, if we evaluate f dashed at a little bit to the left of c and find it's negative, and then evaluate it again a bit to the right of c plus a bit, and find it's positive, then we know that we've moved from a negative through a zero and up to a positive derivative. In other words, the curve has this kind of shape to it, and it must have a minimum down there at x equal to c. If the opposite occurs, if we evaluate the derivative to the left and find it to be positive, and then to the right and find it to be negative, we've got something like this. In other words, the curve has this sort of shape to it around about x equals c. And we must have a local maximum at that point. On the other hand, if we find that the sign of f dash doesn't change at all, if it's positive and then positive on the other side, or negative and then negative on the other side, the point must be one of those inflection points that we're not particularly worried about with extrema. This here is exactly the first derivative test. It's evaluating the derivative to the left and the right of the critical point, which we've already found, and checking how the value changes. Let's try it out with an example. Find the critical points of y equal to x cubed minus 3x squared minus 9x plus 12, and then classify them as either maxima, minima, or points of horizontal inflection using the first derivative test. Pause the video now and have a bit of a go of this one yourself. Come back in a couple of minutes and see if you get what I get. Okay, so in this example, I've actually given you a picture of what the function looks like just to help us out from the start. We'd expect that we should get a maximum here at something like -1 or -2, and a minimum, local minimum of the function, over here at around about x equals 3. Now our first step in actually checking that that's right is to find the critical points of this function. So let's do that. The first thing we need to do is find the derivatives. So dy dx, looking at our function y up here, is going to be 3x squared minus 6x minus 9. Critical points occur where the derivative is 0. So we set the derivative to 0. 0 equal to 3x squared minus 6x minus 9. And that implies, using the quadratic rule, that x1 and 2 will be equal to negative b, which is 6, plus or minus the square root of b squared, 36, minus 4 by 3, which is 12, by 9, which is 108, with a minus, all over 2 times a, which is 6. Now if you evaluate that square root and simplify that, you should find that that gives you either 1 plus or minus 2, in other words 3 or minus 1 for your x values. So for this example, critical points occur at x equals 3 and minus 1. Now looking at our plot, that is exactly what we'd expect. There's roughly 3 there and minus 1 there. So we're off to a good start. Now we need to classify these using the first derivative test. Now remember what that means. We need to find the derivative and evaluate it to the left and the right of each of our critical points separately. See if it changes, and if it does, how does it change? Does it indicate a minimum or a maximum? So I'm going to set up a little table here. For the critical point x equals 3, I'm going to look at evaluating f dashed of x at, well, 3 I already know f dashed of x is 0 because it's a critical point. But a bit to the left and a bit to the right. I do need to be a little bit careful about what a bit means. The thing we need to make sure is that we don't go so far that we're moving past the other critical point. So pretty much anywhere in this region and over here is fine for this particular one. So I've just chosen 2 and 3 because they'll make the evaluations easy. Now remember that f dashed or y dy dx is 3x squared minus 6x minus 9. So what I need to do then is evaluate that derivative, or f dashed, when x is equal to 2, and I'll find that that's equal to minus 9, and when x is equal to 4, so plugging 4 in there, and we find that the derivative is equal to 15. So we can see in this case we've changed from a negative gradient through a 0 gradient onto a positive gradient. So we can see the shape of the curve is going to look something like this, and our critical point x equals to 3 is going to be a local minimum. Now following the same process for our other critical point, x equal to minus 1, we know that when x is minus 1, the derivative is 0 because it is a critical point. Let's just look a little to the left. Again, I'm going to just use integer values, minus 2 and 0, making sure that I don't go past the other critical point. When we evaluate the derivative at x equals to minus 2, we'll find that we should get f dash is 15, and when x is equal to 0, we'll get minus 9. So in this case, we've gone from a positive to a 0 and then down to a negative gradient. So in this case, we've got a local maximum going on in our function. So I can conclude that x equals minus 1 is a local maximum of the function. And that's exactly what we expect, jumping back to our picture. A maximum at x equals minus 1 and a minimum at x equals 3. So everything seems to check out. And our method seems to be working pretty well. The thing about the first derivative test, though, is that it is a little bit messy. We've got to do all these little evaluations to either side. We need to know that we're not crossing over into the other critical point space. It can be a little bit messy like that. So there's another test which we'll look at in the next video in this series, the second derivative test. And sometimes it's a bit better. The thing about the first derivative test is, provided you do it right, it'll always work. Anyway, for now, attempt all the exercises in the worksheet and make sure you're getting some practice with this and knowing how to figure out what these critical points are, whether they're maximum, minima, or points of horizontal inflection.